Hello, everybody. Can you hear me?
Yes, perfectly.
Yes. Okay. I'm going to begin. Hello, I am going to present my work, which titled Effect of Curvature on the Dynamic Behavior of Carbon Nanotube Reinforced FGM Shells. My presentation plan is divided into three main parts. The first part is the introduction, where we will see the allotropic form of carbon nanotubes property and application, and functional graded material. Second part is the study of the vibration behavior of FGM shells. We will see in this part the description of the analytic model and the results of this and discussions. And we will end with a conclusion. Carbon is a chemical element that has several aspects and is present in all living organisms, such as DNA, protein, and oils. In its pure natural state, carbon exists in two crystalline forms, diamond and graphite. This situation changed prominently in the 1918s with the discovery of the third allotropic form of carbon, Oran and scientists. This molecule can contain 10 to 100 carbon atoms in the form of cage or tubular geometry, such as single-walls nanotubes or multi-walls nanotubes. CNTs have several properties, such as chemical properties. In this area, they can be used as a cage from other chemical compounds to manufacture a nanowave. For example, they can also have electrical properties, since they are mainly low temperature supraconductor or semiconductors. Regarding to mechanical properties, they are 200 times more resistant than steel for the weight 6 times less. CNTs have several applications. As an example, we see a biological application. It's possible to obtain CNTs with the molecular graphite or to the surface, which make it possible to obtain a molecular detector for the dosage of molecules on the bodies. In second application, a medical application, in these fields, single-wall CNTs are used in cancer treatment after having been functionalized with specific human antibodies. Application in nanocomposite. In this field, they are used fillers or functional fiber in composite materials to improve their mechanical, electrical, and thermal properties. The functional graded materials, FGM. Nature widely used materials whose properties change with thickness. This is the case of the structures of bonds, teeth, or plants fibers such as a bamboo. As a result, a new class of composite materials was created in the late 1918s by a team of Japanese researchers. Functional graded materials are advanced composite material whose thermomechanical properties vary according to a continuous or discontinuous function law throughout the thickness. Thanks to the special structure of this material, it is possible to avoid a stress concentration at the interface and to improve the mechanical and thermal properties of the parts by combining materials. Since CNTs have mechanical, electrical, and thermal performance, they are used as reinforcement to form nanocomposites. The improvement the composite is due to the size and weight of the reinforcement. In this part, studies of the behavior on the vibration behavior of low curvature FGM shells, the description of the problems in the geometry of the low curvature shell of the FGCNTs is shown in Cartesian coordinate in this slide. A shallow shell can be defined as a segregably curved plate whose smallest radius of curvature are each point is large compared to the greatest length measured along the average surface of the shell. The motion of the shell due to any type of loads is defined by Love's equation. Changing the variables in this equation leads to the following equation of motion. Knowing the moment of the link-up to the transverse displacement by the following expression, and according to Hamiltonian principle, it's amount to neglecting the inertia in the plane and introducing the stress function phi such that, and considering this equation and substituting the equation in by this, we obtained the following equation of motion, a new equation of motion, and according to Bogdanovich, a second equation can be obtained from compatibility condition of shells at low curvature. And using the Galerkin approximation, the expression for the transverse displacement and stress function are written such as by replacing this equation in the first two questions, we obtained the following system of nonlinear nonlinear differential equation is obtained. When we reduce the previous equation of motion, we arrive at the second order differential equation with damping and forcing. An approximate solution for this system of equation is obtained using the multiscale method. We express the transverse displacement W and Nm in terms of difference time scale. To express the approximity of the excitation frequency to the fundamental natural frequency, we introduce the derivation parameter sigma, and we increase the damping and excitation amplitude. After substituting the previous equation into each other and solving the differential equation, we obtained the following equation, and by orthogonalization, we obtained the modulation equations, where alpha E is the effective nonlinearity given by this equation. In the following from this equation, then alpha E it's very infinite when WEG is 2W11. To concretize the previous development, a program in MATLAB has been developed and which is based on the following step. First, we establish the equation of the distribution of CNTs. Next, we choose the distribution. We determine the mechanical properties of FGCNTs, choose the shell geometry of the shell, and calculate of matrix A, B, D, and K. We establish the expression for transverse displacement WEG and the stress function phi EG using the Galerkin approximation. We can calculate frequency and the natural frequencies. We display this last ones and we calculate the effective nonlinearity alpha E, and we display it as function of a number of modes. And we can calculate also the displacement A, which when we display the sigma as a function of A. The properties of the FGM's constituent used for the calculation are given as follow. The vibration behavior of shells, sorry, the vibration behaviors of shell at low curvature is described by the following non-dimensional natural frequencies omega bar. In order to examine the effectiveness of this method, a double validation was carried out with other studies in terms of non-dimensional frequencies. First, the results of our models are compared to those presented by Algeria, based on the nonlinear theory of shallow shells. Shorfi, which developed the theory of first-order shear stress, and finally with Mochogana model based on the Higger order two-dimensional theory. This table shows that the values obtained are very close to result of Alijani and Mutsugana. It is seen that they are not significantly different from the result of Shorfi. The preceding expressions are also are used to Higgins the influence of the effect of the number of modes retained in the Galerkin approximation on the currency of the calculated response, as well as the effect of the distribution of the CNTs on the dynamic behavior of the FG shells. This table showed the parameters used in these studies. The number of modes retained in this approximation is 10 modes. The estimation of displacement as a function of the deviation parameter, as well as nonlinear effective use the following equation. The following figure or slide represents the variation of non-dimensional natural frequencies for shallow shell of unidirectional distribution as a function of curvature kx, ky for the first 6 modes. It is clear that for each mode, the frequency vary remarkably depending on the curvature. To explain the influence of curvature on the effective nonlinearity, we have shown the alpha E as a function of number of modes and plotted for the uniform distribution of FGCNTs and for 12% fibers. It is remarkable that all values of alpha E are less than 0 for the spherical shell kx, ky equal to 10, which indicates that the shell is in softness state for all 10 modes. Unlike other curvature, we notice values of alpha E greater than 0, corresponding to shells in stiffening states. The displacement as a function of sigma for the first mode is it's represented in this slide. We notice an increasingly stiffening behavior as we go towards the right. the equal to ky equal to 10, given a softening behavior, increasing the number of modes from 1 to 2 increase the bending of the curve to the right, indicating and increased stiffening. And for the curvature kx, ky equal to 10, a more stiffening behavior observed from the beginning of the curve to the left. And in conclusion, from our studies, which consist to developing an analytical model allowing a forced vibration analysis for gel with functional graded low curvature reinforced by carbon nanotube, we can conclude that the validation show then the obtained are very close to results of the literature. The three-dimensional plots have shown the dimensionless frequencies depend on the values of the curvature and the number of modes retained. 3. For the CNT's unidirectional distribution shell, we observed a more significant stiffening behavior for cylindrical curvature. However, the spherical case can give a stiffening behavior with more significant curvature. And finally, the stiffening and softening behavior of the shell was clearly influenced by the number of modes and the different type of curvature. And thank you for your attentions.